welcome again. I'm not sure how many of you were also in the session last week. We did the exploration of this data. It's not really necessary. You should be able to understand what we're doing today. Maybe not everything about how I built the data structure and stuff like that, but today we will build upon what we saw last week in exploration, and we'll try our hand at modeling this data to really try and make sense of it. There's a lot of press on it these last couple of weeks, where people were predicting stuff that didn't really come out, or they used a much too naive prediction. And we will probably see why that happened and how to approach something like this in a responsible way. Let's put it that way. So. Okay, I hope you're all in for another hour of a lot of information and analysis, and we'll see where we get. I've got so much to tell today that perhaps again I won't be able to fit it in 1 hour, and then we'll just do another session next week or the week after to continue with this. But we should be able to cover quite some ground today. So welcome again. I have the chat open on my second screen, so if you see me looking sideways, I'm looking if there's somebody who has a question. So ask your questions in the chat. I'll try to keep an eye on it, and perhaps people from IBM in the session can also have a look there and interrupt me if needed. If you really need attention or you want to discuss something, feel free to unmute yourself and just ask the question and see if we can get into there. So yeah, let's go. So last week we built a data structure on the data that I downloaded from EU CDC. So that is the European Center for Disease Control. That's where you can easily download an updated Excel sheet every day. So what they do is they publish every reported case and deaths per country per day. So that's what you can download there. And we use that data to build data structure and do all kinds of analysis on that. So so please, if you still want to look at that session, it is published on YouTube, and you can have a look in the past sessions of the Meetup to find that session. So what I'll do today is I'll run through that data again, but now from more an analysis viewpoint, where we really want to understand what's going on in the data, not just looking at it, but also trying to find some kind of pattern, which is typically what you do in a data science project. What I didn't mention last week is that just about every project or proof of concept that I did in my practice as a data mining specialist, I always saw a project like that as a data enrichment. And that means that the analysis or the data mining or data science step is just one step in a whole process of processing data. The data comes in, gets processed, and ends up on somebody's desk, maybe as a file or as a graphic that person then uses to take decisions on. So basically it's decision support, what you're trying to do. So that's also the approach that I use here. So the visualizations are just for analysis. And what I'm trying to produce here is a enriched data set, which not just contains the current data and the historical data, but would also contain future data, predicted data. So somebody can look at that and say, okay, I see this trend, the forecast for next week is this and this, so I can try to make policy on that. That's quite a responsibility to provide that kind of forecasts, because somebody might base policy on it, and it might not be reliable, it might not be relevant, it might not be significant in a statistical sense. So you really have to dig in and find out if what you're doing is being built up in a responsible way. So that's what I'm trying to do on the side as well. But remember, I build a data structure and I try to enrich it with extra data that I've found out from past data. So if you just run through the first steps, I'm importing the Excel file here. It looks on the server for a download. It says, okay, for today I already downloaded the current session, the current version of the data, so it's not really necessary. I need a couple of libraries from Python to do the analysis. So pandas is basically for manipulating data structures and getting them in the right format to analyze. And I'm using numpy as well, which is the numeric library available to Python, where you can find all kinds of mathematical and numerical routines that you can use on your data. So I read the data into the Excel file into a data structure for pandas, and I just check what comes out, and I can see that the most recent data is from May 14th, so it's yesterday's data. Today's data will be available most of the times between 12 and 12:30. So what I'm doing now, because what I just said is I'm going to try to enrich this data, I need extra columns to put in the predicted data later on. So what I'm doing here is I say, okay, I've got these two columns, cases and deaths here, which are the newly reported cases for that country on that date. And I need extra columns here to add my data that I'm going to predict, that I'm going to forecast. So I add two columns, P cases, P deaths, for predicted cases, predicted deaths, and I put them to null, to not available, not a number. So there's nothing there yet. So just by doing this statement, saying, okay, my data frame needs a column called P cases, and I'm going to fill that with not available. This creates two extra columns in the data set, which will be later on available for putting in predicted data. So I do a count on it just to check if all the data came in right, because last week I already told we had some not available data because of import problems. But I see that all the fields are filled. I've got the same count on every column. And I've got nothing there yet for predicted cases and predicted deaths, because that's logical. I just added them, and there's no data in there, but they are there. So that's just a check here, and that's also one of the things out of my practice. When I do something like adding columns, I always check, are they there, because something might have gone wrong, I might have missed an error or whatever. So always check. That's and double check and triple check, to be honest. Then I'm going to pivot this data like I showed last week. So now all the data is in one big data set, and all the countries are below each other. And I'd like to have the countries in columns. So I can compare, and I can simply select a column for a country. So I pivot the data set, which more or less works the same as in Excel. You just pivot based on an index, which is the reporting date. I tell them what I want in the columns. That's my countries. The geo ID is this one. That's for example for the Netherlands NL. And I want values. So that's what I need in the cells of this data structure. Are the cases, the deaths, the predicted cases, and the predicted deaths. So I built up this big data structure, which you can show a small preview of here. I've got my date as an index, so it's all indexed by date and accessible by date. I've got main sections that are cases and a couple of others to predicted deaths. So there are 4 of those sections, and in each section I have a column for the country with the data for that column, for that country, for that measure, on that date. That's what I just built here by this pivot statement. So now I've got this big data structure with a lot of room for predicted values. You can see that not all the countries have values. So for example, there was no data for country for AG at this date, and you can see that all the predicted values on the right here are all unavailable because there's nothing there yet. So a lot of columns now, but well, don't really that's not really a problem. I mean, you can have lots of columns and still have good performance in this kind of structures. Now I added extra columns for predicted data, but predicted data is obviously data in the future. So I also need extra rows in my data set. So I need to add rows there to put in data for dates that are not there yet. So this data structure now runs from last day of last year to yesterday. So I need extra rows in the data set to be prepared for putting predicted data there. So this is a bit of trickery with pandas, where I say I want a new index on the data set, which is a very easy way to extend your data set. I say I want a new index, and I say I want to start at the minimum value right now. That's the new index starts at the same date as the old index. And the other end of the index will be this here, which says I take the current maximum date, which is here. So it's the index maximum. And I add a time delta, which is a pandas statement, which can help you very easily with calculating dates. And I say I add a time delta of 91 days. So I add 3 months of empty rows to my data set. So previously I added columns for the countries, for the measures that I didn't have yet. And now I also add rows to be able to put data somewhere for the future. So now I've got this whole prepared data structure with extra rows and columns for the data that I'm going to generate. And that is also comes back to what I just said. At the end, when we have predicted lots of stuff for lots of countries, you can simply write this data structure back to an Excel file, for example, and give to somebody and say, okay, here I've got all the predicted data. So that's basically what we are trying to do here. So I just check a couple of things. Well, we're obviously going to use some numerical algorithms to try and generate new data, which is all numerical. And most of those algorithms don't know how to deal with a date. So for us, it's very easy because we can simply see the date here as an index column and we can select by date. But most of the numerical algorithms need something like a number. So what we do here in this whole statement here is that we are converting the date that we have as days since, and I just took an arbitrary date in the past, 1st of January of 2019. And I want the difference between these two, and I want that expressed as an integer. That's basically what I do here. So I say I take the difference between the current date in the index, and I see how many days did pass after the first day of 2019, and I make an integer of that. And just to describe that here, to show what came out of that, you can see that, for example, that the minimum date here was 364, which is logical because I started at the 1st of January, and the first date that we saw in our data set was the last day of December. So it starts at 364 and the maximum is 590. So now I've got an extra column with day numbers so that I can start calculating that stuff without using the date algorithms of pandas, because I'm going to use the numerical libraries from numpy, and they cannot handle dates. So this is something that you see a lot, obviously, when you're preparing data for analysis, that you have to change some data formats and stuff like that. So now I have a day number at least. So let's just check what is usually applied in this case for looking at this kind of distributions, which we saw last week, is a Gaussian function, which is a function that is based on a probability distribution that's below. And Gaussian functions have this kind of shape, which you can see here on the Wikipedia page for Gaussian functions. That's a first approach. You might right away start screaming that it doesn't really run this way and it might be a bit different. But this is a first approach to find out if something would fit a Gaussian distribution. So that's the formula that we're going to use here. And then the nice thing, and that's also why it's used a lot of times, this kind of distribution, is that when you start calculating with this, you can easily reduce it to a more simple form. So we're going to use a little bit of high school mathematics here. So I hope you still can remember a little bit about logarithms and derivatives and stuff like that. Not that much, I promise, but we'll have to look into the function a little bit. So basically, the nice thing about trying to see if something fits a Gaussian distribution is that if you take the logarithm of that function, it becomes a parabola. So it becomes a function that you can more easily analyze. So let's try that. So we take for a couple of countries here, selecting them as we saw last week. Let's run all the cells above here to be sure that we have something that we can continue on. Right. So when you draw that function for a couple of countries, in this case Italy, Spain, France, Belgium, the Netherlands, and we're looking at a bit of smoothing, which we saw last week as well. So I take the rolling average over 2 weeks of the data to make a bit of a smooth curve to visually inspect it. And I use a logarithmic scale on the y-axis. So I'm going to compress this axis. You can see here that it's not just numbers, it's powers of 10. So every difference between two ticks is 10 times as much. And you can see that for a couple of countries which we have here, apart from the first bit of noise that we have here for early outbreaks, which are very small, to be honest. I mean, that's just 10 to the power 0. So this is just very low amount of cases. You can see that you have something that might approach a parabola here. So it might be something that you can approach with a numerical function that way. So that's what we're going to try. So we start with my home country, with the Netherlands. That's for a couple of you as well, I guess. And what we can do is what I usually do is I create a separate data frame to start generating data for that country. And then when I finished and I'm happy with the way that that prediction comes out, I copy that data frame into the larger structure that I have to be able to export it later. So I create a simple data frame for that country. I've made this all variable, so you can easily tinker around with it. Again, all this code is available. I'll again post the link in the meetup afterwards. So I select the country. I select the measure that I want to look at. I want to look at cases in this case, and my predicted measure would be predicted cases. So this is just to be able to be very flexible. So you can if there would be all kinds of other measures, or you would do a couple of predictions, you can easily change this variable and do another prediction for another value. So I'm going to do in predicted cases, I'm going to predict the cases for the Netherlands. That's basically what I say here. So I build a simple data frame, which I call a data frame prediction here. And I build it for the X values, for the X-axis of my graphs. I use the day number that I generated before. So this is just days since the 1st of January of last year. And for the Y value, I take the measure here, the measure that I defined, this measure, for the country that I defined for P cases. So that's the easy thing in using pandas, that you can simply say, okay, I want to have this measure for this country, and you can express it with a simple statement like this. So I take, in this case, the cases for the Netherlands, the measure for my country. Yeah, then I want to filter out this bit of rubbish up front here for the country that I'm looking at. So the start of this graph is a bit of local infections before the real outbreak started. So I'm only going to select rows in that data frame here where there's more than 100 cases in this situation. This is a bit of an arbitrary number. We'll see later on how we can use this for different countries. But for Netherlands, in this case, the number 100 works all right. We'll come back to that later. For now, we take only the days where more than 100 cases were reported. And then I take the logarithm. So here I showed the graph of this data using a logarithmic scale, but now I really need logarithmic data. So I need the power of 10 that is used here, because as we saw, when I reduce my Gaussian distribution by taking the logarithm, I get a parabola. So that's something that I can try to fit a curve to, because for an exponential distribution or a Gauss distribution, that's pretty complex. So I take the logarithm and I plot it for this country. So I take the logarithm base 10 of my y-axis and I plot that simply. So you can now see for the Netherlands here, because I left out the cases below 100, I've got something that might be a parabola. So that's looking familiar. Well, then you can take the next step. I always say people start screaming about artificial intelligence, machine learning, using all kinds of algorithms. In this case, it's not that simple. So you might wonder, why don't you just use some clever AI algorithm and apply it to the data and try to fit it? Well, the answer to that is that the AI algorithm wouldn't know where to start. It wouldn't know what to fit. So if you just fit it, for example, on the first bit of the curve, it would simply say, okay, this is going exponentially. So if you are trying to predict data for a country which is not peaking out yet, which is not yet at the top of that curve that you are expecting, it will simply predict something that goes exponentially and keeps going exponentially, because the algorithm that you're using doesn't know anything about countries and disease and the way that these things usually run. So you have to put in some knowledge of yourself. That's basically what I'm saying here. And then the other thing is that I always say, always first try regression. Start with the most simple mathematical approach that you can use for trying to fit and predict your data. Because of that, if that works correctly, then you're there. Then you don't have to do anything complex and something with deep neural networks that are hard to explain and hard to understand what's really going on there. So that was basically my approach here as well, that I say, can we do this with a simple regression? And then later on, we can build on that. So this is not something that we can do with a simple linear regression because it's not a line, but it is a parabola. We know that's a parabola. So we can, if you remember from your high school mathematics, you can take the derivative of a parabola would be a line. There's a function for that. So the first derivative should be a line. That's what I'm saying here. And there's a gradient function in numpy which you can apply to data, and it will actually tell you what the first derivative of your data is. So it looks at the angle of every set of points, and it would follow this curve here. So then you get the first derivative, which should be something that looks like a line. So this is that one. This is the first derivative of that data using the gradient function from numpy. And you can say, yeah, well, there might be a line there. That's something with a lot of noise, obviously, due to reporting delays and stuff like that. So probably this low number here is somebody who forgot to deliver data, and then all the data was delivered the next day, and then again, and you always have a weekly effect in your data. There are more cases reported on Tuesdays because that's when the weekend cases normally are reported. So there's a lot of noise in that data, but we could try to fit a line. Now, the nice thing is that there's a function for that in numpy as well, because it's, fitting a line to a set of data is not one of the hardest things to do. But there's a function for that. So there's the function that is called polyfit. So we can simply say, okay, I take all my x values, and I take my gradient values, which I've put in a column called G above here. So I take all my x values and all my gradient values, and I want to fit a curve here with a first degree because it's a line. Second degree would be a parabola, and third degree would be a third function, and so on. And I want all the details of this fit. That's basically what I say here. So here I call a function, which is, you could say, a kind of machine learning algorithm because it uses linear regression to fit to the data. So this is my first algorithm call where I say, okay, try to fit a line to this kind of data. Then I get the results of that. So I'll just run this cell here because we need that G column for the next one to run. And then we run this here. And what you get here is visually you say, okay, it's the polyfit function tried to fit this data as best as possible with a line. And you can say it's really, it looks okay for now. Apart from the noise, it looks like this data can be fitted pretty well with a line at this point. And basically what I'm doing here is I use polyfit to create the vector for this line. So the slope and the intercept to create this line. And then I actually applied those values, which you can, where there's also a function for. So the results from polyfit, you can put into polyval, which will calculate the values based on that fit. So I ran all my x values here through the to the x values, and I drew the line that came out of that. So here I have my regression line, which is called R, and I've got the original gradient function, and I show the line. So looks pretty good. Now we can do the same trick. There's a question from, he says, is there some meaning to the slope of the fit line? Yes, there is. Sure. The question is, what do these values mean, that there's a slope and an intercept to that line? Obviously, this is one of the values that you can then calculate back to the original Gauss function, because the Gauss function, if we look at that, has a certain mu and sigma. And you can calculate the slope of the line back to the corresponding mu and sigma values, which would show you how steep and how small and how high the resulting Gaussian function then would be. So you can use those if you really calculate them back to what they would mean as the parameters of the Gaussian function. So yes, there is, but the actual numbers for this line are far away from practical usable values, but you could calculate them back. I haven't done that yet, but was planning to look into that. So if you can fit a line to this data, we should also be able to fit a parabola to the original logarithmic data. Now that's what I'm doing here. So I'm doing exactly the same trick here. So now I'm using not the gradient values, but the y values. And I say that I want to fit in degree 2. So I want a quadratic function to be fitted to this data. And that's pretty straightforward. We do exactly the same thing. And now we get, I create a column which is called P for parabolic values, which is using the fit that we just got on the x values. And when I plot that, you can actually see that that kind of data pretty well fits a parabolic function. So now I was able to get at the 3 parameters that I have now for the parabolic function. Because that's also something that I miss when I just do the regression here. I just get the shape of the Gauss function in the end, but I don't get the scale of the Gauss function. So I actually need to fit to this parabola to get to actually get three things, which also include the scale of the function to see how high it would actually get. Well, so this is a parabolic fit to the data. So now I could use that to recreate from that parabola. If I take the exponential again, because this data was I took the logarithm. So when I take the exponential again, I get back to my original data. Well, that's basically what I do. Here I say, and now I'm going back to my original data set to put in the right values. So for the predicted measure for that country, I take 10 to the power, because that's the reverse of the logarithm that I did, 10 to the power of that fitted data based on the day number. So now I'm in my original data set and I say, okay, the fit that I found, I'm now going to apply to my original data. And then when you plot that, it starts looking pretty well, to be honest. So here you see the curve for the Netherlands. So the blue is raw data, and the orange one is the fitted curve for that data. You can already see some deviations, which we will get into, but this is more or less the best fit using a Gaussian function that I can have on data for the Netherlands in this case. So this means if you accept this as a fit, which you shouldn't do just by I value, you should analyze a lot more before you start actually using this for predictions. You can see that we are in the first wave, and I hope it stays a first and only wave in the Netherlands. You can see that we are already quite far, and probably somewhere in June, the last cases from this first wave will be there, and we will be over the first wave of infections for the Netherlands. That's basically what we see here. But pay attention, it's not that easy, and that shows when you try to start fitting this to other countries. If you have this kind of distribution, which shows the current cases and tries to predict the curve for future cases here, you can also do a cumulative display of that to get the distribution of all the cases added together, and you can again see more or less where we are in the cumulative curve. So the curve that I fitted actually predicts flattening out from more or less the 1st of June in 2 weeks, and it flattens out at about 42,000 cases or something. But you can already see, and that's something that should worry you, that the actual curve here, which is blue, which are the actual cases, is already above that, and looks like it's going to rise further. So this might be a nice fit on the start of the curve, but something is going wrong here on the end, and you can see that even more. So you see the last figure, so it's 43,000 predicted now, 43,000 cases, but you can already see we are already above that, so something is not going well here, and you can already see that a little bit in the curve here, that the slope at the beginning seems to be steeper than the slope at the end. And if you take a country that's even farther along the curve, so let's go all the way back here and start with a country like Austria, for example. We just put AT here and run all the cells again. Then you can see this is the line for Austria. This is the parabola for Austria. This is the fitted curve, and you can see it going wrong there. You can see that it tries to fit as best as it can for the whole data set. So here it underestimates, here it overestimates a little bit, here it underestimates again, but it tries to optimize the curve to fit on the data set as a whole. And that's something that's going wrong here. And if you look at the cumulative data for Austria, you can see where it's going wrong. You can see that it can really well fit the start of the outbreak, but then something goes wrong. So originally I thought maybe this is because of the measures that are being relaxed in Austria in this case. So you need some background research for that. Then I thought, yeah, maybe somewhere first or second week of April, they already started relaxing their measures there. So that might be an explanation for that it doesn't run as usual. But when I tried a couple of other countries, that wasn't really explaining the problem that I had here. So for example, if you look at DE for Germany, Deutschland, and I run all this, oh, sorry, I run all the cells. That was the wrong click. Hang on, yes, run all the cells below. Then you get the whole stuff for Germany. So you get the line, you get the parabola. You can already see, does that fit all right? And here you see the effect for Germany. They have a much longer tail already than in Austria. And you can see that when you try to fit a Gaussian function to that, it really starts to optimize over the whole function, but it doesn't. But locally, it doesn't really work anymore. You can see that clearly in the cumulative curve here. That wouldn't work very well in this case. And that's worrying, because if you look at a country like Brazil, for example, which are still at the first days of their outbreak. So we'll run below. You can see the stuff for Brazil, the line. You see there's only the start of a parabola there. It's just the beginning of the curve. You can see that it fits the beginning of the curve very nicely, like it did in other countries. But if you just saw what happened in Germany and Austria, I wouldn't use this rest of the curve as a true prediction. So it seems to hit their peak at somewhere in half of June and then go down again. And it fits very nicely on the beginning of the curve. You can hardly see the blue line because it fully overlays the orange line. And you predict here, for example, that they will end up at something like 1.1 million cases in the end, which maybe goes a little bit further than that even. But you can already see the problem. If you try to predict data for Brazil with this line, they will also probably run out of this curve and end up much higher. And that's one of the things that went wrong in the United States, for example. A couple of weeks ago, somebody drew a Gaussian curve for the United States when they were still in this stage here at the earlier stages of the outbreak, and then predicted that they would only have 50 or 60,000 deaths or something. And then everybody said, "Oh well, that's not that bad, and we can handle that, and should be no problem." But then they quickly started running out of this curve. So they based their approach, they based the relaxation of measures in the United States on an approach like this, and you can already see where it goes wrong. So yeah, that's basically that we just concluded that the start of this outbreak runs very nicely like a Gaussian curve. So you could use that to model the first bit. But it's not good enough for modeling the rest of this. And there's a big warning attached to that you shouldn't use something like this naively to immediately base measures on it. It can go very wrong. So then, yeah, I was just wondering what is, and also my colleague Edward, who's also in the session, helped me with that quite a bit. What kind of distribution is used in epidemiology? I mean, this is just a mathematical distribution based on probability distributions, like there's a certain probability that somebody will infect somebody else, and you can base a distribution on that, and that will go this way. But in practice, it seems to run differently. And then from quite some literature, we came on the gamma distribution, which is used a lot in epidemiology to model the outbreak of diseases. So basically adding more knowledge to the way that we try to fit this data really helps. And you can already see there's a couple of examples here on the Wikipedia page for gamma, and you can see that what it does for certain values, it really has this nice steep slope in the beginning and then this relaxing slope at the end, which is also something that we see in our data for the countries that are already some farther ahead in the curve. And you can see here this would then be the cumulative distribution function, which for a gamma function usually goes way further than just the end of the Gaussian function. It's a bit more complex using a gamma distribution. I really had to dive into some basic statistics and probability again to try to understand this stuff. And it's not as easy as just fitting a line, because the gamma is quite a complex function, and that goes for the cumulative distribution function for sure. It's not that easy. So then I started diving in how could I approach this kind of fit, and I found out that in numpy, in the numeric library that we have that we're using here, there actually are fit functions for all these kind of curves. So we're not doing it by hand anymore, by reducing it to a line and then see how we can fit that line to our data, but just by using a accepted method to fit gamma curves. So that's what I'm doing in this notebook. All these notebooks are available again. So I'll just run a little bit through this and see how you would approach using such a standard function in this case. So same steps here for building my data set. So I'll just step through that. Basically, I'm doing exactly the same here, preparing the data set for using predicted functions. Okay, and then it becomes different. I use Austria here because we saw that Austria doesn't really fit the Gaussian data very well. So let's see how it would work with the gamma kind of data, the gamma kind of curve approach. The problem here is that if you're using more a distribution or process-based kind of curve fitting, it's not that easy to prepare your data set to actually use it, because it doesn't look at, for example, what you have with Gauss, that everybody has a certain probability to infect somebody else. Basically, that's what's below that kind of approach. But here you say, I'm going to look at the distributions, the distribution of the days, the number of days since the outbreak. And you say, I'm not going to see how many people were infected by somebody else, but I'm going to say, how probable is it that somebody would be infected 100 days after the outbreak, or 50 days after the outbreak, or 20 days after the outbreak. So basically, that's the approach that you're following here. So you have to transform your data set here into something that shows for every case the number of days that case took to really get infected. That's basically what you're doing here. So you're not looking at probabilities anymore for the infection. You're looking at probabilities for the number of days that you would expect since the outbreak that somebody gets infected. So then for the low number of days, for example, 10 days after the outbreak, there will be very few people. There will be a lot of people in, let's say, 30 or 60 days after the outbreak, and there will be very little people 100 or 200 days after the outbreak. That's basically what you try to model here. So it's a bit of a different approach, and that's also why you need different data there, which is a bit of a bother, to be honest, to get your data in the right format. So here I'm doing the same again. I look at Austria, I look at the cases and the predicted case, and I'm going to predict cases here. I made my prediction data frame here just the same as we did before. I used the day number and I used the measure for that country that I'm looking at. Then I'm saying I'm only using the days that were reported above 0. And that is because these fit functions that I'm going to use here, they cannot handle missing data. So I'm only going to use the days from that data set where there is actually some data, where there's a number of cases reported below, above 0. Then I need a separate data frame in a different format, because this is just X and Y values for day numbers and countries. I need a fitted data frame, and that's a bit of a complex thing, because what I actually need here is a data set that doesn't say I've got this number of cases for that day. So it's not a grid anymore, but I need a data set that just is a linear data set, just a one-dimensional array. And it actually lists the cases for every day. So I have to convert my data and say, I'm not saying on day 10, I had 1,000 cases. I have to convert my data set to a format which now says I've got the number 10 1,000 times. That's basically what you're doing here. So you convert your data set from saying for day 10, I have 1,000 cases. You convert it to I have a data set where the number 10 actually appears 1,000 times. So there is 1,000 people which have 10 days before they get infected. So it's a bit of a bother, but there, well, you can use some Python tricks to do that. So the expanded data, which I'm preparing here, actually says I want to repeat. That's a function from numpy, which is pretty easy to use in this case. I want to repeat everything that I have in the first column of my data. So that's the day number. Python always starts counting at 0, so 0 is the first column. Everything that I have in the first column, I want to repeat by the times I have in the second column. So here I actually say for the day number that I have, I want to repeat that day number in this example that I used 1,000 times. So you get a very long data set with all the case numbers in there. So for larger countries, this will be a pretty big one. So if you have 1 million cases, you actually get a factor here, an array with 1 million entries in there. So that's, but basically it's just number crunching. So there you go. So this, but that means that if I now plot a histogram of that data, where I say, where I do the reverse thing, and I can simply use a plot where I say I want a histogram. That's what the kind is says here. When I plot a histogram of this data, just to check if my conversion went right, it should look a little bit like the original data. So here again, I say, okay, the number 430 appeared that kind of times, the number 440 appeared 2,000 times, and so on. So here I've got just a check to see if what I just did still represents the original data. Well, then I can use SciPy, which is a very well-known library for Python as well, which contains all kinds of scientific functions. And there is actually a gamma fit function in there. So there's a stats library in there, and I'm going to use stats gamma fit. So I'm just going to fit a gamma curve to this kind of data. Oh, I see a remark from somebody that my sound is not well. Can you hear me again, Edward? Or I guess everybody can still hear me, or otherwise I would have more mentions of that. Okay, anyway. So here we're going to do that fit. So we're just going to use that basic function called stats gamma fit, and I'm going to fit that to the data set that I now have, to this expanded data set. There's a couple of technical values that I'm going to take out of that. Let's not go into too much detail. You can always dive into that if you're interested. So the values that come out of that, I can use the reverse function of that fit, like you saw with the linear fitting with polyfit and polyval. We now have a gamma fit, and on the other on the side we have a gamma PDF, which does the other thing. It takes the inputs that we have generated here and it applies them to the data that we have. So here I basically fit everything that came out of that fit function, which are 3 parameters for the gamma distribution: alpha, location, and scale. And I fit them to the data to see how that would come out. So here you go. This is the fit for Austria, and now you can see that it really nicely starts fitting this steep approach here. It doesn't really take the peak very well, and then you can see that the outside of that is much longer than the start. So you can actually see that's not symmetric anymore, and you can probably see that the gamma function would, in this case, better fit the data than what we originally did, because we don't assume anymore that it's symmetrical, and we can find the way that it's not symmetrical, which is called the kurtosis, which is one of these values here. You can find that out from the data, basically, in this case. So if you do the fit on the cumulative function, so where do we end up in this case, you can see that it pretty well fits. It's not always a perfect fit, but you wouldn't expect that to be honest. So this already works quite a bit better than the Gaussian approach that we used. So yeah, then the question obviously is, we now use a country which has pretty much of that curve already. Can we use this data for other countries as well? So we could try, for example, the Netherlands, to have a look at how that would fit our country. Run all below. So this is the distribution for the Netherlands, which looks pretty much like the original data. And you can see that we have a pretty good fit here. We're starting to run a little bit out of it on the right side here. And that's also something you can see here as well. You can see that it doesn't fit the end maybe as perfectly as it could, but it seems all right. And then that's also where I find this gamma distribution in literature, which shows you that if you have the outbreak behind you, so you have the full curve of the outbreak, you are very well able to fit a gamma curve to that. And then from the gamma curve, which has stuff like standard distribution, standard deviation and mean and stuff like that, you can easily start calculating all kinds of parameters of your past outbreak. And yeah, that's a bit of a letdown, because you see that in the Gauss function, we assumed that the end of the curve would be the same as the first of the curve, and that enabled us to see how the end would run. So if we try this for a country where we actually don't have an end of the curve, for Brazil, for example, so can we use this for prediction, is more or less what we're saying here. And I run all the cells for Brazil. Well, you can see that they're still at the beginning of their curve. That's what you see from the histogram here. And you see that it doesn't work for Brazil. And again, that is because the gamma function assumes that you have the whole curve available, and it wants to fit on that whole curve. So actually, this is the best fit that we can get to the data of Brazil. It overestimates quite a lot here. It underestimates quite a lot here, which more or less cancels out in the fit. And you see that, yeah, it's a very nice approach to modeling afterwards and finding out all kinds of parameters about your outbreak after the outbreak. But it is not very well capable in predicting the curve, because you don't know where you are in your curve yet. So it just tries to fit on the whole data set. And then the cumulative curve for Brazil in this case would look something like this. It would assume that you're already at the end of the curve, and it would fit the function to that. So it doesn't really work for prediction in this case. And that's something I see in news and research and stuff all around at this time, that you could use gamma very well for approaching the outbreak afterwards, but it doesn't really work very well for predicting. So just the countries that are already far along, so a country like Switzerland, for example, you can very well fit that, but it doesn't really work for the countries that are still in the first stages of their curve. So here you see Switzerland, for example, which already shows this nice flat out at the end. And you see here the fitted curve for the cumulative data. So that works. So yeah, there we are again. So we first tried a bit of a naive approach, to be honest. Then we tried the approach from literature with the gamma curve. But the problem here is that one of the parameters of the gamma curve is how much the right end of the slope is different from the left end. And if you only have the left end, you can't really say anything about how the right end is going to run. So that's a bit of a problem here. It's near 12, so I'll just give you a glimpse of what I'm working on right now. But for now, I'll just first keep my mouth shut for a couple of seconds and see if there's any questions right now. So ask them in the chat or unmute yourself, and we can maybe have answer a couple of questions or have a short discussion. Good question. I get the question for China's curve. So what I can do is obviously just put China here. So this is the data for China, very steep one and a little bit of an end curve there. And you see there was a problem in the China curve where they suddenly reported 15,000 cases, but So probably I have to smooth that out, but you can see that the fit runs reasonably well. You see that China is at the end of their first curve. Here you see this big bulge where they suddenly reported the 15,000 cases extra, but it fits reasonably well to the data that we know right now. So that works out reasonably well, and we should do some kind of smoothing to take out that peak of data here. What I've done is for each of these approaches, I've also got a notebook which is called multi. So for example, I've got a gamma multi notebook, and what I did there is, because I took a very generic approach to modeling per country. What's different between this and the other notebook is that there's not much documentation here. So you use the first notebook to try to understand what's going on, and you can use the second notebook that's also there, and you can just input a lot of countries in there. So for example, this is the notebook for the gamma distributions. And what you can see, I just put a big list of countries, or you could even uncomment this and take all the countries that you can find in the data set. You get a lot of graphs then, and you can simply draw the lines for all those countries. So if I run this whole notebook, if you have questions about quite some countries, you can simply run this notebook, and you get for each of the countries you get the results. It takes a while because for some countries there's a lot of cases, and as I said, I have to build this huge one-dimensional vector containing all the cases for that country. So it's now doing the US, which is already way over 1 million. So that takes a while. So this is just an example where I just put in some interesting countries. I mean, you can run this on the whole data set if you want to. And what I'm always also doing here, I mentioned this number 100, where I say I only count the countries over 100. I now also try to base that on the population of that country. So if the population is much lower, I already count days with lower amounts of cases. So you get the data for all these countries. My laptop is a bit busy at the moment, so it takes a while. So you've got the fitted numbers for all these. This is just more or less progress indicator. And here you see for quite some countries. So if you want to look at quite some different countries, you can use this notebook. So for example, this is Japan, which is already quite ahead in the case. You see that it doesn't really work on Russia because Russia is still in the first stages. It works reasonably well for the US, but not yet, because there's going to be a long tail here probably. So yeah, if you want to look at quite some countries, you can just run this notebook and have a look at all these countries. And yeah, if you want, you could overlay them on each other. It's now separate graphs, but so you can. This is where I concluded that this gamma approach didn't really work for all countries, to be honest. So what I did in the let's see, I've also been experimenting with smoothing a little bit, because I saw that problem obviously from China, where they suddenly reported so many cases for one day. So I also in the multiple notebook for the Gaussian approach, I already experimented a little bit with smoothing as well, where I don't take the raw data, but I take the average data for 2 days, for example. So here, for example, if you look at Brazil, you can see that I've got my original data in blue. I've got the smoothed data in orange, which is a bit more smooth. It takes the peaks out a little bit, probably needs more. And then it also does the predicted cases in green. That's basically, so you can experiment around with smoothing the data in this notebook if you want to. I'm not sure if China is in here. I don't think so. So let's see. I'll just China on top here. And there's a problem there. It says hang on. So run all the cells. Data coming in. So then you have, let's let's see. Okay, there's going. Yeah, oh, I remember. There's something. It filters out quite some noise in the approach here, and that doesn't work right for China right now. So we'll have to look at that again. So have a look, I would say, and see where we can improve. Because then I've already moved on to the next step in modeling. Corrected this in the end, but anyway. Yeah, there's quite some stuff here if you want to, and if you're into this stuff, you can experiment around with different approaches to modeling this data, and also looking at maybe ways to smooth this to get the right curves for more countries. Right, so now it's we're around 12, so I'll just give you a glimpse of what I'm working on, which is another distribution, which is called Gumball. And I really had to dig to find out what it would be used for and why that would be interesting. And to be honest, I found the Gumball distribution, which is also approaching the way that this kind of data runs. There's not much practical experience in using this kind of density function to model epidemiological data. That's always a different word to pronounce. So it comes more from extreme value analysis. So the Gumball distribution is used, for example, if you look at river heights, and you say every year I'm going to record the maximum height of the river, then if you do that over a lot of years, then the distribution for those maximum heights will be a Gumball distribution. That's the underlying thing. So it's a bit hard to translate that to epidemiology, but there's quite some approaches already that are looking at that. And basically what you're doing is you're saying everybody is in contact with each other in a population, and actually the fact that somebody gets infected is an extreme event. That is something that's an exception. So you model the exceptions of all the contacts between all the peoples, and you say if somebody gets infected, that's an extreme event. And then the number of days before something like that happens is actually what you're analyzing. So basically that's a bit of the background behind this way of modeling. And yeah, to go a little bit ahead, this seems to fit really well on all kinds of countries. So for example, if you look at the approach for the Netherlands here, you can see that kind of distribution fits really well on the data. And it also fits quite well on countries which are at different progress in their outbreaks. So for example, if you take Brazil here, and you run this analysis for Brazil, you also actually get, because of some optimization routine that I put in there, you actually get the progress of that country. So Brazil is right now at 13% of their outbreak. That's basically what I'm trying to do here. And I have to do that because I need to fit the data to the right place of the curve. So here you see it looks a little bit like the original Gaussian approach, because I draw a line which I try to fit with a linear regression, and then I calculate it back. And if you then fit the Brazil data, you actually get something that looks quite realistic. It fits the data very well, and you see that it has this long tail that will probably be seen in the data, because if you fit this to other countries which already have this kind of tail, it fits very well. But there's still some stuff that I have to research here to see if I'm really doing something that's suited to the data, but you can really start drawing conclusions on that. But you can see here that it fits most of the countries extremely well. So if you put Austria in here, for example, let's see, where's my, there's also a multiple notebook here. So if you want to look at a lot of countries here, be my guest. So if you put Austria in here, you can see that it starts fitting quite well. You see that Austria is already almost at the end of the first outbreak. It's at 99.5% of the outbreak. So that's already way ahead. So here you see the distribution for Austria. You see the line that I'm trying to fit, which nicely fits the data. And here you see the actual curve that was fitted. So probably also some smoothing needed here, because here we go way above and here we go way below. But if you look at the curve here, you can see that it actually fits pretty well. And because they're already almost at the end of their curve, you can see that that they're actually you can actually see that they're already at the end of the curve here. There's hardly anything going on here. So yeah, that's it for today. Way over 12 o'clock already. What I'm looking at right now is, because if this approach seems to fit most of the data, then you can start looking at the ways that it doesn't fit very well. For example, Austria started a bit steeper and goes a bit slower at the end. You could maybe try to link that to the way that the country actually approaches the outbreak. So the measures that they take, and if things like that help or not. So that's going to be the next step, where there will be some machine learning probably as well. Right. Any questions for now? Well, not in the chat, I see, and it's probably also because I overloaded you with information again. So I would say I've recorded this session, so I will trim it and blur it again and put it up on YouTube, so people can have a look at it. I'll post the link to all the notebooks again, and the link is also to the environment that you could use to run these notebooks in, or you could run them locally on your own system. And I'll probably schedule a session, I guess, after next week with some more machine learning, and see if we can in any way link this to the behavior of people in the country, and say what we see about that. Okay, that's it for now then. Thanks for attending again, and hope to see you in probably not next week, but I guess the week after.